Alright, so where were we? We just reached asymptotic optimality with some arguments based on sort of making the lower bound into an algorithm. Okay? So then, let's see if this helps. We get unstuck. No. There is a power on it. Excellent. Now it's green and buzzing. Okay, so let's try to make an algorithm that is maybe a bit faster and that has guarantees for finite delta to get rid of this asymptotic. And as some of you already envisioned, it will be based on looking at this as a saddle point problem and solving it with iterative methods. Okay, so drag and stop, it was based on doing a plug-in estimate of the oracle weight, where this was this expression for these oracle weights. And so let's first talk about how do you actually implement drag and stop, and then make it smarter. So one way of doing it is to just say, okay, I need to solve this saddle point problem. Good. So I take two learners. One controls the W, one controls the lambda, and I have them interact with each other until it's approximately converged. And then I get my saddle point and I will use the W. Okay, so that's a way to compute this W star. Right? And you might say, well, but your objective is not concave convex. The problem is lambda. It's a horrible mess in lambda. The domain is not even convex. And depending on the divergence, this might also not be convex. Although for Gaussians it would be. But we will always, at least for now, look at the lambda player as being second. And that means that we don't really have to worry about this curvature behavior. We can just do best response anyway. So whether we would sort of convexify it first and then do best response and get a point, or whether we just go for the best point is the same. Okay? So one way to instantiate learners would be you need a simplex learner for W. So you could use some adaptive version of hedge if you want. And we need best response for lambda. Okay? So this is like the user interface now. The user needs to give us some implementation of this argument. Okay? So if we input weights and a bandit model, it gives this argument. Okay, so that would still be a way to compute drag and stop as it was defined. But so in lambda it's horrible, but in W it's great. Yes? Yes? Well, you might be tempted to think that, because for Gaussian it would be a square, it's great. But the domain is already not convex. So you are really in trouble. And once you go, let's say gamma or something, it's not convex in lambda either. So, if you would just do a textbook thing, you'd say convexify. Go to distributions on this neg I star. But then if you realize, what am I doing when I do best response? You're still going for a single point. So in the end, you can just do best response on the lambda level. So that's what we will do. But you can only do this because you're playing second. Outside, you have to do the learning. Inside is the lazy player. Right? No real learning there. Okay. So what are the inefficiencies that we might sort out? So, first thing is that we are computing W star at a plug-in estimate. The plug-in estimate is noisy. So that means that it probably doesn't make sense to compute W star super approximately. Super precisely. Anyway. So we need to know, can we stop early maybe to do less work? And then when you update by one sample, you actually don't move a lot in new head. So maybe you can actually reuse most of the computation so far and don't redo it. Okay? And we would like these finite constant guarantees. Okay, so how are we going to get all those things? So the main idea is, instead of every round run from scratch this saddle point interaction, we're not going to restart it ever. So we start our saddle point interaction, we run it for one step, and out comes the W, right? The iterate of the W player. We use that in the Bandit to select an arm. Back comes a sample. We update our mu head. We change the objective while we're going, because the objective involves a mu. So there is a plug-in estimate. We change the objective of the minigame, and then we do another iteration. And it turns out it's enough to do just one iteration for every Bandit sampling step. So that's very nice, that you don't have to do batches. Okay, so we will advance the saddle point solver by one iteration for every Bandit interaction. Okay, so this is maybe a bit of a diagram of what it will look like. We have these two learners. One is learning a distribution over arms, call it the K learner, for example, ADA hedge. One of them is doing best response. Best response is this expression here. Right? So out of that interaction, you're building the loss function, and that sort of translates into feeding a gradient into ADA hedge. And out of ADA hedge comes some weights. Right? So those weights, you feed it into your tracking module. That outputs an arm. You use that arm to request a sample in the Bandit model to get an observation. You use that to re-estimate your mu head, and you substitute that back in the problem up here. No, so we do one iteration of this that just advances the two learners a little bit. So we're never solving. Wait, okay, sorry. So the yellow one, we are solving it exactly. Yes, but as a result, the saddle point one just improves a little, and then it gets estimated, sort of updated, so it changes what it is, and then you improve it a little bit again, right? So it's sort of in lockstep, slowly spiraling into control. That's sort of, yes, yeah, because it's a minimum of linear. Right? So in that variable, it's nice. Okay, so now let's try to do some proofs about all this contraption. So I'm going to sort of cheat and simplify, but I want to give you a high-level picture of what's going on. And how I think about it is that there are a lot of things that have to be controlled simultaneously, right? So there are the tracking things, concentration argument to go from mu head to mu's. There is the regret bound of the learners. We have to take care of exploration, for which we use optimism, so that also generates some overheads. But the good thing is that all these things sort of stays somewhat modular and just add up overheads as you go. And then at the very end, you see that all that was still order square root t, and it doesn't really affect the main term. Okay, so no. Well, yeah. Good. Yeah. So of course, when I promise you, I have a finite delta guarantee, my first response was to actually put it on the slide, right? But I found out it's not even spelled out in the paper. It says, solve this problem and you will have your guarantee. And then it looks approximately like this. Okay? So this, I think the second term will probably be square root of this next door. Yeah. Yeah. So I backtracked and said I will just stay small, but now present this as a finite delta guarantee. But of course, it's like a weird move, right? But it was just unsuitable for a talk to actually put what it is. So you can show that you get the right main term, and then you get a horrible junk, which is then smaller. Okay, so let me give you a little hint of that compositionality thing that I was claiming. So, how do you do that? So you want to show the sample complexity is small. And the way you do it is you start from the stopping rule. So you say, if I haven't stopped yet, that means that my GLRT statistic is still below my threshold. Right? I cheated, this should be mu hat. I put in the mu. Okay, forgive me. So from the stopping rule you get this. Then you use tracking, so that means your ends are actually looking like sums of W's. Okay. Then this is an info for lambda, but you use the regret learner for lambda, so you can replace it by the iterative of the lambda. Okay. Then this is also an expression where the player plays W's, but those W's are designed to have low regret compared to the best single arm. So that allows you to go to the max K. And then here you still have some like sum of weighted stuff, which is in some sense a distribution of the stuff, which you can replace by T times the best distribution of the same stuff. And now this looks like a min-max, but it's actually the flip of the max-min W lambda that we saw before. Right, so this is the value of that optimization problem. And what this says is that the stopping threshold, which was more or less log 1 over delta, is more than the number of samples we're at times the characteristic time-related thing minus some small stuff. Right? And now you see that it is basically linear in T here with some smaller order square root T stuff here. So if you solve and you wonder how large can T still be for this to be true, you get that it's log delta over the value here. Okay, so that's roughly what you need to do for this type of proof. Okay, so yes. No, so currently there is no tracking. Instead, what happens is the two players are interacting. Every time a W comes out, interesting. Yeah, yeah, we still need to track. Yeah. Yeah. Oh. I'm not sure you would want to, but maybe you can. Yeah, so one nice variation that you can do, sometimes at least, is to flip the order of the players, to actually have a learner for lambda. I said that domain is complicated, the function is complicated, but sometimes it is tractable to make a lambda learner. At that point, you can do best response over here. That's nice because it's always a single arm. You can just directly play it. We played with these variations in the paper. Okay, so proof of the pudding. Does it actually work? So the answer is yeah. So we ended up actually showing more that the alternatives work much worse than showing that we are so great. Okay, so here is a standard problem, like best arm, on which prior work was done. So that's the one for which track and stop had all the proofs in the original paper. Okay, so we just made up some bandit model, took some reasonable delta, 0.1, it's actually quite big, and try to see, do the asymptotics actually kick in already, right? It's reasonable. Okay, so what you see are a whole bunch of algorithms, and then for each of them I have a box plot of the running time. So you get some idea of the distribution of when you stop. The star is the mean, and you see some, like, everything outside is like a dot. Outside, I guess a 95% or something. Okay, so what is ours and what existed? Track and stop is T, so that's those two. So you see direct tracking works better. Okay. Our algorithms are the first four. So, for example, this guy, it's close, maybe a little bit worse. Playing the oracle weight directly, as you were asking, is the purple one. So you see that that's not stellar in any sense. And yeah, so if you take the lower bound seriously, you get blue. If you use the threshold that we actually put in the stopping rule, which already has sort of lower order terms, and figure out what that should tell you about stopping, since you're not going to stop earlier than that, then you already get the red one. So that's maybe more representative. So in the lower bound, you really have a log 1 over delta and nothing else. But in the stopping rule, our threshold features these lower order terms. And if you take those into account and solve for the time that you would stop with those, you get this one. Right? And then uniform sampling is blue. So that's sort of really done. That's supposed to be this one. Okay, so I guess the main benefit here is that our computation is much cheaper. We're like 100 times cheaper than doing a full saddle point solution every round versus just one iteration. Okay, so now on to the example where we make the competition look very bad. So this is it's a minimum threshold problem where you're supposed to answer, is there an arm below the threshold or not? It's just two arms, 0.5, 0.6. Threshold is 0.6. So the answer is yes, there is one. It's the first, for example. So the optimal weights are just sample that low arm all the time. And now what happens is, picture is that everyone is sort of okay, except for track and stop. But what happens for track and stop? The box plots look fine, which means that most of the time it's stopping at the same time as these guys. But the mean stopping time is excessive. Okay, so it depends a little bit on delta, how excessive. If you make delta, let's say 0.1, the mean is really up there. And what's happening is, suppose you estimate the first arm a little bit high. You think it's above the threshold. Then you think, Jesus, this is a super hard problem because arm 2 is very close to the threshold. So I have to figure out if it's below or above. I have to answer that to give an answer. So you sample on arm 2, and it won't help you because it's at the threshold. Right? So the forced exploration has to, at some point, get you out of this mode and make you see that arm 1 is below the threshold. And that forced exploration, it goes very slowly. So that's the reason for these sort of rare but super long runs that are making the mean explode. Okay, so the conclusion is the asymptotics for track and stop, in some problems, they really don't kick in for practical delta. Yeah, so I already made it crazy small, and then even then it doesn't work. So I have the same picture for the smaller one, but then it's just even higher. 0.1, I think it's off the scale here. Okay, so in that sense, these algorithms are safe. Okay, so let's conclude this part. So pure exploration, I would say, is sort of, there is a new flavor of algorithms based on these lower bounds, and they are able to match the instance complexity. So that's new and that's different, so that's interesting. Things have been worked out for quite a lot of problems, like implementing this oracle. So we are getting a bit greedy. We'd like to do complex queries, maybe even solve reinforcement learning problems, sort of by sampling, figuring out the optimal strategy in an MVP, for example. Okay, so one way to think of this is that it may be a useful submodule for some bigger system. Okay, so there are a few things that I did not talk about that are quite interesting. So what if there are multiple correct answers? For example, epsilon best arm. It's surprisingly different what happens. And there is a different line of algorithms based on a variation of Thompson sampling. That has led to only in 2 cases algorithms that are, at least I believe, matching the lower bound as well. So top 2 Thompson sampling for best arm and Murphy sampling for minimum threshold. Yeah. Although, yeah. Okay, so maybe things to highlight about what's still missing, particularly the third point. I hid for you these glorious finite delta terms, but you can ask, like, are they actually so small that I don't care about them for practical delta? And at least in theory, the answer is no. So you might then hope that still it runs well. So I showed you some experiments that say it's at least not doing crazy stuff. But it would really be nice to figure out get bounds that really give you the right answer for moderate confidence. But for that, we don't even have the sort of a credible candidate lower bound. Okay, we have several lower bounds, but they don't even agree on what is the main term. And, yeah, it's a mess. Okay. Good. So let's also say some things about part 2. Yeah. Just keep sampling for a while from the same one. Yeah, so these WTs, I think they are quite stable. So if you keep them for a while, or if you update them, I think you will be sampling from the same roughly WT anyway. Oh, the inner one. Ah, okay. Yeah, that might shave off some more. Yeah. No. Yes. So one way to think about is that they don't match the lower bound. So in the experiments, they might. I wouldn't be surprised if they work at least equally well. No, yeah, LUCB. They have a different notion of optimality. Okay, so I want to say a few words about the other task, regret minimization. So what's changing? So now samples are not just information to us like they were before, but now they also represent reward. Okay? And it's the goal of the algorithm to collect as much reward as possible. Okay, so now it's expensive to sample an arm that is giving low reward. And in this world, the metric of evaluation is called the regret, and it's the maximum reward available minus the reward that you collected. Okay, and the go-to algorithm is UCB, and when you run that, you have a logarithm in T regret. Okay, so that's the baseline that you will maybe get in the university course. Okay, so what I want to do right now is focus a little bit more on structure. Okay, so let's go back to this example where we have some profile of qualities of drugs. And what I want to get to is something that looks like this. So I want to have algorithms that have a log T regret, but the factor that multiplies log T is informed by the structure that I impose. Okay, so if you look at my little graph here, you will see that it's an instance of unconstrained, it's also Lipschitz, it's also modal, it's also concave. And with the right basis functions, it's even linear. Okay? But as you go down the hierarchy, you get more and more information, ruling out all sorts of possibilities a priori that you don't have to worry about, meaning that you should be able to actually improve your regret. Okay? So I want this adaptivity to the structure in my algorithm. Okay, so we saw the interaction already. There's nothing much different. There's still a multi-arm bandit. Now the time horizon is fixed, T rounds, and we have this regret evaluation criterion. So every time you sample an arm, you incur what's called the gap, which is the difference between the optimal arm you could have sampled and the arm that you picked. Okay, so we want to keep that under control. Okay, and we'd like to get asymptotic optimality as the first step, then finite time regret guarantees on top, and we would specifically like to know, can we make something that sort of the structure is sort of a nice parameter, you supply something about it and it adapts to it. Okay. So, yes. Yes. In some sense, we are now back to always best arm, because we just have to sample the highest reward. That's our task. So all this talk about query structures and answers, etc., it evaporated. But what still remains is that I can give you some prior information about the set of bandit models in which we are working. So that is that structure, Lipschitz, etc. Sorry, can you say this start again? No, I don't know how to give the notion of a query a meaning when your task is to care about high reward. So, yes. Yes. So it, so I think what I heard you say is, why don't I separate what I observe and my sort of choice of maybe even an answer, right? So then you're right, when you decouple that. Yeah. Yeah. Yes. So maybe this is more of a like following the history traditional thing. Once you decouple observation and action, you are getting very quickly much closer to the full information case. So the fact here that to see something, you have to also get its reward, makes seeing bad stuff very costly. If I decouple where I look and what I do for reward, then the fact that I can randomly look and not be charged for it makes it almost as if I can just see everything. So it's a strange. Yes, I'll add it to the to-do list. Maybe there is a reinforcement learning mini game to be discovered. Okay, so I'm going to run over a little bit. Is that a big problem? A few minutes. Okay. So. Oh, okay. So it's not like 2 minutes. Good. Great. That is helpful. Okay, so the rest of the structure will be very similar to what we did before. We will go over a lower bound. It's not the same one, but it has another min-max problem inside. Then we will look at can we make single round interactions give us what we need from that lower bound and build algorithms from that. Okay, so the lower bound for regret is actually interestingly much older. So what you do is like in the pure exploration case, you need to make an assumption about the algorithms that you're searching over. So they cannot just know magically what mu is, for example. Right? So previously we said let's make them delta correct. Here we're going to say let's only worry about algorithms that are asymptotically consistent. What does that mean? That means that if you put them in a bandit model, they will sample the suboptimal arms not very much. And how that's typically quantified is subpolynomially, which you can think of as just log, but maybe a bit more. Below any polynomial, below any power of t. So you really don't sample them a lot. But we want to sample them only logarithmically, because then we will have a chance to match the log t regret rate. Okay, so in that class of algorithms, we can play again that similar game by saying, look at a bandit model mu and another bandit model lambda, where the best arm is different. So I star is now always best arm. So being asymptotically consistent means that if I put you in mu, you will sample the best arm for mu almost all the time. You can only spend very little on all the other suboptimal arms. So when you divide by t, it has to go to 1. Okay? Whereas if I run you on lambda, you have to sample almost all the time the best arm for lambda, which means you don't have any time to sample the best arm for mu. So that proportion goes to 0. Right? So we have two bandit models in which your algorithm has to do something very, very different. Okay, so that means it needs information to see that difference. Okay, so you can quantify that by a nice sort of Kullback-Leibler contraction-based argument. But what comes out of all that is that if I look at how many times you sampled an arm, and I look at how much information you get from seeing an observation between mu and lambda, then that has to now be at least log t. Okay, so that's what happens between mu and lambda. So that's for a fixed lambda. Now we can sort of optimize over the lambdas, and then we still have these counts for how many times the algorithm samples each arm. And to get a lower bound, we can give it sort of the smartest possible way to set those counts. Okay, so if you follow that argument, you get this expression for the regret lower bound. It says, under the constraint that for every confusing alternative lambda, you have at least log t information to discriminate it. That comes from the previous slide. We are going to look at your regret, which was the sample counts times the gap. Right? And we will optimize by giving you the smartest possible allocation of samples. So that's a lower bound on the regret of any algorithm. Structure here means, I don't know if the word is present. For me, it's always the mu, the set mu. Did I write it anywhere? Oh, yes. Okay, so it's just a word for the set mu. It's the constraint of where our bandit models come from. The set of bandit models that we assume. Okay? So this is now our new problem. Currently it's written as a single optimization of some linear objective with a constraint, but you can equivalently write it as a zero-sum game if you want, by bringing this constraint over. Okay, so we'll see that in a moment. So what happened before? People were going along the same lines as drag and stop. They said, okay, at each point in time, let's compute the optimal sample count of every arm for a plugin estimate you had, and then make sure that our actual sample count sort of advance toward that. Okay. And then we have to make sure that our mu hat actually converges to mu, so we add forced exploration. Now it's sort of one of the very funky differences is that forced exploration has to be itself at a rate lower than logarithmic in t. Because log t is sort of the main term, so you really don't have any exploration, really. Asymptotically, okay, but in practice you have like 4. Right? Okay. Good. So what we're going to do is we'll reformat the lower bound as this mini game again. We'll solve it iteratively. We use what comes out to advance our sample count. We'll force exploration somewhat differently with optimism. And then we again do this composition where we put everything sort of in a long chain and get our finite time now regret bound. Okay, so what about that minigame shape? So as we said before, the lower bound, which I write here Vt, was of this shape logarithm of t times something, and the something we can now express it as a min-max problem. So if you put the constraint in the objective and you reparameterize not by the total number of counts of each arm, but by the proportion, so to introduce these W's to bring it closer to what we have, it becomes a max-min problem, but the objective is a little bit different from what we had before. When it was not regret, but pure exploration, it was just the numerator. Right? But now it's sort of information per unit regret that we are seeing. Right? On the bottom, this is a regret. Okay? So it will be convenient to rewrite it slightly. The reason is that this is now not a nice function of W anymore. Right? W appears top and bottom. So it may still be quasi-convex, but it's not convex. So we really don't like it. So let's parameterize instead by the proportion of regret of every arm, instead of the proportion of samples that you put. Once you do that, it becomes a linear in the new W tilde. So that's great again. So this is like a candidate for feeding it into our saddle point solver. Right? And if you really want to, you can also swap min and max. That's maybe nice if you have a good learner for lambda and you like to just get a single arm every round, so you don't need any tracking. Okay, but I'll be working with the middle one. Okay, so maybe just as an illustration. So I started out with this profile of arms here. So you now can compute what are these optimal proportions under a different set of constraints. Right? So the constraints come in the set over which you search for your lambda. So that's where they appear in the problem. And you see, for example, that if it's an unconstrained problem, yeah, it's curious, but you have to sample the best arm almost all the time. So that one is sort of not so interesting. It's the proportion of everybody else that you need to sort of carefully tune. So in an unconstrained problem, you need to sample everyone else with some carefully chosen proportions. And for example, if I tell you it's unimodal, then it's enough to sample the arms neighboring the optimal one. Right? The reason is that if you sample those and the optimal one, you see this tent shape, and because you know it's unimodal, you have identified the best arm. So you can get by without any samples from these two. one additional arm next to the best one. Right, and you can also, there is an int lambda that we will end up needing to implement. So here is a picture of what that looks like. So in blue is the best arm, the instance where we are at. And for example, if I ask what is a concave hard lambda, so concave is purple. So the current best one is I have to make someone else the winner. And here you do it by moving this arm up to be higher than the existing one. But for example, if you do it Lipschitz, then you see that for Lipschitz it's apparently cheaper to move this one up to become the winner. But then the Lipschitz constraint forces you to also move this one up. Otherwise, this would be too steep. Right? So you, depending on your structure, you now get a search process for finding these alternatives. Okay, so what's the overall structure going to look like? Very similar as before, except the learner here will now work on the regret proportion level and not on the count proportion level. So that learner will output a W tilde for us. Okay? So we have to map that desired regret proportions to desired pool allocations. So that's new. Tracking, sampling, estimate. And this is the same as before. Okay. So again, it's sort of unfortunate that I can only do a little bit of justice to the thing. So let's look at what happens if we cheat grossly and say, let's not worry about any estimation, let's just run this scheme on the actual mu and see what happens. Okay. Yes, because they are a function of mu and we don't know them. So that complicates things a lot. And they appear in ratios. So we will even need to estimate some d over some delta. Yeah, so that might it creates lots of nasty stuff. Okay, so what's happening if we do this? So we're cheating. We're actually running everything on mu. I call it the noise-free case, just to see what's happening. So we run our algorithm until we satisfy the constraint. Right, and then after that, all the other samples we can put them on the best arm. We have enough information to know it, so that doesn't cost us anything. Okay, so then the claim is that the regret of the algorithm of this scheme, maybe measured in W just for convenience. Maybe we don't do any tracking right now. We just put the W's here. Is the value of the game plus the regret bound over that min-max term again. Okay, so this is log t over d star. This is regret over d star. Okay, so you might worry now that wasn't regret of order square root t, right? Log t plus square root t, that came over. But you have to think, how many rounds do I actually need to run my algorithm? Because most of the rounds are actually spent on the best arm. They don't appear here. So it turns out that if you're careful, then the number of rounds that you're doing sampling to multiple arms can be itself of order log t, which means that the regret is then of order square root log t. Okay? So that means that in the end, this is sort of a lower order term, and this is the main one. So I think what we do is we say, no matter where you are, there is some minimal distance to the world in which your best arm is different. So every time we do such a sample, we get evidence. And that evidence is itself linear accumulating. But it's bounded by a log. So in the end, yeah, that means the number of rounds can be at most order log. Of course, it's a bit of a cheat because the big O depends on where you are right now. But this is the part of the proof where we are sort of sloppy and dirty because we just want to get home. This could be optimized much more. Okay. So there are lots of interesting things you need to do. For example, turns out we struggled with this a lot, is that the learner, for learning these proportions, if you just feed it this objective function as the loss, right? So you fix the lambda and you look at this expression as a function of W tilde. That was what appeared in the min-max problem. That, it turns out, it doesn't work. So you need to scale it every round by some factor, which involves the algorithm itself. But you're not changing that when you're thinking about changing W. So this is now a fixed constant. Every round is different. It scales your objective. And then we get a regret bound for this quantity. Okay. So that gives you a bound like this. Plugging in instead of the W tilde, the max K. Okay. And for the other side, yeah, so the learner itself outputs the W tilde, which was a regret proportion. To map that to a round proportion, you have to divide it by delta and get a W. And then that W is used for tracking, and it's also going into the computation for the other learner. Okay, and then you can bound this thing again by the threshold at which you're stopping. Okay, and so the final result is that if you add this regret overhead and this log t, and you massage what you get, turns out you again find your min-max value, which was this d star, times the regret now. So that's where these round factors are useful. They become this regret. Okay, so that means that if you reorganize, you get that the regret is bounded by 1 over d star, which was the log t over d star, which was the value, and then the b over d star. I don't know why there is like a line in the image. Okay. So far I've been cheating just to make it more palatable. Let's just say some words about how you uncheat the whole thing. Everything I showed you so far was with fixed mu and knowledge of the delta. So, gross cheat. Okay. So, what we used, what I showed you right before, you can already use it to compute a saddle point solution. But now we want to use it in interaction. So, let's overcome some of the problems. So, one of the problems is there are these gaps. And of course, the gap on the best arm is 0. Right? But I was freely dividing and multiplying by it all over the place. So that is actually not working. So we fixed that by cheating, or inside our algorithm, putting a minimum on all the gaps that we compute. So we estimate them and then we bring them off of 0. So that creates a perturbed vision of the problem. A funny vision in which there is no arm with 0 gap. But it turns out, at least for small epsilon, you get the right quantity. So now it becomes a tuning question. How small do I need to make it? And you can actually be sort of more precise about how close you get when epsilon gets small. Okay, so that's one trick. Then we replace mu by mu hat. So we're going to incur all sorts of concentration terms. We like to have to explore, so we do it with optimism. And so here are maybe asking some upper confidence bounds on the thing that is actually in the end the gradient in our problem. Okay, so it's a d term over a gap estimate with a clipping to some epsilon, and then with some sort of optimization of the actual point over a confidence set for the parameter. So it's like, okay, super messy, but you need to go through all these things. And then there is a last problem, and that is that we actually do not know which arm is the best one. So initially we might get even the wrong picture about that. But the domain of lambda uses it. So that we solve by actually running one copy of the whole process for every guess of what the best arm could be. And we only advance the one that we currently think is the correct one. So that creates some storage that we need to have. Okay, so this is when you put everything together what you need to do. It's not for consumption. So, but I think the overall idea is sort of completely the same between the two. It's just much more complicated here. Okay, finally some experiments. So I was telling you, I want log t be red, and I want the constant in front to be what the problem tells me, the lower bound tells me. Okay, so here are some experiments to that effect. So the first one is a structure that we call sparse, which says all the arms are the same except for one, which is